Hello learners, in this video we are going to see quadrature phase keying, quadrature phase shift keying. Here, the main aim of quadrature phase shift keying is to utilize the bandwidth efficiently. This is the main aim for quadrature phase shift keying. Here, the carrier phase in binary phase shift keying, there is two phase, one is 0 and another one is pi. Here, the carrier phase taken four equally spaced value, that is pi by 4, 3 pi by 4, 5 pi by 4, 7 pi by 4. The transmitter signal is defined as Si of t is equal to square root of 2e divided by t cos 2 pi fct plus 2i minus 1 pi by 4. Here I value is equal to 1, 2, 3, 4 and t value is ranges from 0 to t. Here E is the transmitted signal energy per symbol and T is the symbol duration and Fc is equal to Nc divided by T. Nc is the fixed number of integer and if we expand the function we will get Si of T is equal to square root of 2e divided by T cos 2i minus 1 pi by 4 cos 2 pi Fc minus square root of 2e divided by T sin 2i minus 1 pi by 4 sin 2 pi Fc. Here there is two function, one is in phase function and another one is in phase function and another one is quadrature phase function. Here I value is ranges from 1, 2, 3, 4 and there is two orthonormal function pi by 2 pi 1 of t and pi 2 of t. Here pi 1 of t is equal to square root of 2t divided by cos 2 pi fct and pi 2 of t is equal to square root of 2 by t sin 2 pi fct. Here the t value is ranges from 0 to t and here there is here the two symbol is transmitted at the same time. If the symbol may be a 0 0 or 0 1 1 0 1 1. If the symbol is 1 0 means the region is Z1. If the symbol is 0 0 means the region is Z2 and if the symbol is 1 0 0 1 means the region is Z3. If the symbol is 1 1 means the region is Z4. This is the decision boundary and this point, message point is equal to here. The phase of the qpsk signal is 1 1 means it is 5 by 4, 0 1 means it is 3 pi by 4 and 0 0 means it is 5 pi by 4, 1 0 means it is 7 pi by 4. The coordinate of message point is equal to 1 1 is plus e by 2 plus e, s1 s1 1 is equal to plus e by 2 s1 I2 is equal to plus e by 2 square root of e by 2. And similarly, we will write 0 in means it is minus square root of e by 2 and si2 is equal to plus square root of e by 2. If it is 0 0 means the angle is 5 pi by 4 and the joining point is here. If it is 0 0 means the angle is 5 pi by 4 and then the message point is minus square root of e by 2 to minus square root of e by 2 and if the message point is 1 0 means at the time the angle is 7 pi by 4 at the time the message point is equal to plus the square root of e by 2 to minus square root of e by 2 and generation of qpsk signal. In this generation of qpsk signal, it has the binary signal is given into the polar non-written to zero level encoder. That encoder output is given into the demultiplexer. Demultiplexer divides the signal into odd signal and even signal. Odd signal is given in upper side we give the odd signal and lower side we will give the even signal. In this odd signal and even signal is multiplied with the orthonormal basis function. The orthonormal basis function is pi 1 of t is equal to square root of 2t divided by 2t into cos 2 pi fct and the even function is multiplied with pi 2 of t. Pi 2 of t equal to square root of 2t divided by sin 2 pi fct and these two signal is added and the resulting qpsk signal is transmitted through the channel. In coherent direction, it uses pair of correlator. This is the one pair of correlator, and this is the another pair of correlator. This is the in-phase channel, and this is the quadrature phase channel. The common input is given into the two pair of correlator. Here the common input is given into the two pair of correlator, and then this correlator is multiplied with the orthonormal function pi 1 of t and pi 2 of t, and the which means the receiver is synchronized with the transmitter. The output of the correlator x1 is given into the threshold value, and x2 is also given into the decision device. The decision device having the threshold value is equal to 0. If x1 is greater than 0, then the binary symbol 1 is calculated. If the x1 value is less than 0, the decision device decide the value is equal to binary value equal to 0. Similarly, the same operation is performed in the lower pair of decision device, and then then the multiplexer is compare the two binary sequence and produce the output original binary sequence in the receiver side. Error probability of the QPSK. Here the error probability of the QPSK system is operating in the additive white Gaussian noise channel, and the received signal is defined as x of t is equal to si of t plus w of t. W of t is the white Gaussian noise function with 0 means, and power spectral density is n naught divided by 2. Here we use two correlator x1 of the x1. The output of the two correlator is x1 and x2, and x1 value is the integral of 0 to t x of t into pi 1 of t into dt, and x2 of t equal to integral of 0 to t x of t pi 2 of t into dt. If we calculate our correlator output, x1 value is equal to plus or minus square root of v by 2 plus w1, x2 value is equal to minus or plus square root of v divided by 2 plus w2. The decision the device take the decision rule is S1 of t is transmitted if the received signal point is received in the fall in the region Z1 at the time S1 of t is transmitted. If x2 of t is transmitted, if the received signal is signal point fall inside the region of Z2 at the time the receiver decide the value is S2 of t, and similarly if the received signal S3 of t is received in the fall inside the region of Z3 at the time the receiver decides the value is equal to S3 of t, and similarly S4 of t is transmitted if the received signal is fall in the region of Z4 at the time S4 of t signal is considered. Okay, the received signal S4 of t is transmitted, but due to the additive white Gaussian noise, the received signal fall in the outside the region. At the time, the error decision is made. The qpsk receiver has two binary PSK receiver working in parallel with two carrier. One is in-phase signal and another one is quadrature phase signal. In-phase signal output is x1 and quadrature phase signal output is x2. The two binary receiver characterized as follows. The signal energy per bit is equal to E by 2, and noise spectral density is equal to N naught divided by 2. The average probability bit error in phase and quadrature phase is equal to P dash is equal to Q of square root of V by N naught. Here, the average probability correction resulting from the combination of two channel, it is PC equal to 1 minus P dash the whole square. If we substitute P dash, we will get 1 minus Q of square root of E divided by N naught the whole square. If we expand this function, 1 minus 2Q of E divided by N naught plus Q square E divided by N naught. Average probability symbol error is PE equal to 1 minus PC. So 1 get cancelled, we will get the function is 2Q of E divided by N naught minus Q square of E divided by N naught. The exact probability, exact bit rate of QPSK is equal to PER equal to Q of 2EB divided by square root of 2EB divided by N naught. Power spectrum of QPSK signal. Depending upon the die bit sent during the interval minus TB2 plus TB, the in-phase component are equal to plus or minus G of T, and similarly the quadrature phase component also plus or minus G of T. So G of T function is square root of E divided by T 0 to 0 to T. In-phase and quadrature phase component are statistically independent according to the baseband signal. Baseband power spectral density of QPSK signal is equal to sum of individual power spectral density of in-phase and quadrature phase component. So SP of F equal to 2E sin square of T into F. It is equal to 4EB sin square of 2TB F. This is the this is the qpsk function. This qpsk function, this is it is this power spectral is symmetric about the vertical axis, and each every time, uh, and then the power spectral density is equal to 0 for every t time period, 1 by 2 time period. And QAM is the hybrid form of modulation, and it experiences the amplitude modulation and also the phase modulation. In MRA PAM, it is the one-dimensional. It has the one-dimensional signal space diagram. MRA QAM is the two-dimensional generalization of MRA PAM. The two orthonormal function is pi 1 of t equal to square root of 2 divided by t cos 2 by fct. The ranges from t value is ranges from 0 to t. Similarly, pi 2 of t is equal to square root of 2 divided by t sin 2 pi fct, and t value is ranges from 0 to t. And QAM is the combination of amplitude shift keying and phase shift keying. Two different signals sent simultaneously on a same carrier frequency. Here M value is equal to 4, 16, 32, 64, 128, 256. The example of QAM, here we consider 12 different phases combined with the two different amplitude. Here the phase angle is equal to 4 phase angle having two different amplitude. Totally it has a 16 combination, 16 signal combination. Each baud is equal to 4 bit of information. By combining the ASK and PSK, each signal corresponding to the multiple bit, more phases than the amplitude. The minimum bandwidth required for QAM is same as ASK or PSK. This is the signal. Here it will have totally it has 16 combination. Totally it has 16 combination. Here the input signal is given and the amplitude is two different amplitude is given. Here this is the one of the amplitude and another amplitude is this is another amplitude, and totally 12 phase angle is given. 12 phase angle is given. Total possible message point is uh, 2 power 4 16 message point, and this is the phase changes with two amplitude. Here the phases changes and 45-degree changes at high amplitude. This is the 45-degree changes to the low amplitude. Thank you.